Today, what we're going to do is we're going to look at other ways in which we can apply L'Hopital's rule. So L'Hopital's rule was where you try to do the limit, you try to do direct substitution, and you get 0 over 0 or some type of infinity over some other type of infinity, like infinity, positive infinity over positive infinity, or negative infinity over negative infinity, okay, or positive infinity over negative infinity. Okay, so you could have opposite infinities on the numerator and denominator, okay? So here we look at this one. Okay, so what's the limit as x approaches infinity of 2x times e to the negative x? Okay, so if we look at this, okay, and we try to do a direct substitution in here, okay, this is just going to be a really big number, right? So this is going to wind up equaling infinity, right? Because the limit as x approaches infinity of 2x is just going to be infinity times. Now, this is going to be a really big negative value. So that's going to mean like, let's say like a million, right? So this is e to like the negative 1 million. Well, that'd be 1 over e to the 1 million using the negative exponent here. Okay, so that means we have 1 over a really big number, and that would be 0. So what we have here is infinity times 0. And what we can do algebraically is rewrite a product as a quotient, okay? And for this particular problem, we can rewrite this as 1 over e to the x. So we can take this and rewrite it as 1 over e to the x, and then our limit becomes this, the limit as x approaches infinity of 2x over e to the x. And that was just applying the exponent rule. What does a negative exponent mean? It means 1 over, right? Okay, so now if we try to do the direct substitution now, okay, we're going to get the limit as x approaches infinity of 2x, which is equal to infinity. And if we take the limit as x approaches infinity of e to the x, well, as x gets really, really big, right, this is going to go to infinity. So what we have is the situation of infinity over infinity. So here we go. We can apply L'Hopital's rule to this because it's a quotient and the numerator is infinity and the denominator is also infinity when you do the limits individually. Okay, so here we go. So this is equivalent to the limit as x approaches infinity of 2 over e to the x. So this is 2, and as x approaches infinity, this is going to be e to a really big number, which is going to cause this to be a really big value, right? And 2 divided by a really big value is going to wind up being 0. So this is going to equal 0. All right, so that limit is equal to 0. So you may have thought, oh, Mr. Mitchell, infinity times 0. Well, anything times 0 is 0. Not true with infinity. So sometimes when we take infinity and multiply it by 0, we don't get 0. We get actually something else. So it's because this infinity is not really a number. It's the idea of something that's really, really large, okay? All right, now a lot of times I will tell you it will come out 0, but not every single time. So it's not a guaranteed thing, okay? So let's go and look at our next problem. So for this next problem, we're taking the limit as x approaches 0 from the right of 4x squared times the limit as x approaches 0 from the right of ln of x. And this would equal, okay, so this would be 0 here, right? Because if we just do a direct substitution, we get 4 times 0 squared, which is 0 times. And as x approaches 0 from the right of ln of x, that actually becomes negative infinity. Okay, so we have L'Hopital's rule, right? We can somehow apply L'Hopital's rule. So let me show you. It's not like the last problem where, oh, you know, we can rewrite it using exponent rules. We got to do something slightly differently on this one. All right, and what we're going to do is we want to rewrite this as a quotient. That's the idea, okay? And basically what we're going to do is we're going to create a complex fraction. So let me show you what I mean by that. Okay, so we have 4x squared ln of x. And what I'm going to do is I'm going to multiply by, and it could actually be either one, but what I'm going to do is I'm going to make this one, I'm going to get rid of this right here, okay? And the way I'm going to get rid of this is I'm going to multiply by 1 over 4x squared over 1 over 4x squared. And what this is going to cause is it's going to cause a a complex fraction to happen, or and a quotient in that too. So this is equivalent to the limit as x approaches 0 from the right. And here this top would just become ln of x, okay? Or let me go ahead and write, this would be 4x squared ln of x over 4x squared over 1 over 4x squared. Now this 4x squared and this 4x squared are going to go away. So now we're left with the limit as x approaches 0 from the right of ln of x over 1 over 4x squared. Okay, so now what we have is a quotient here. Here's the fraction bar, okay? What happens when we take the limit as x approaches 0 from the right of ln of x? What we get out of this is negative infinity, and the limit as x approaches 0 of 1 over 4x squared. Now we got to think about this. Okay, this is going to be 0. So this denominator is going to be 0. Okay, if we do a direct substitution, but really what it is, it's a really going to be a really small positive number, right? When this is a really small positive number, this is going to come out to be infinity. So we can apply L'Hopital's rule to this. Okay. Now, we probably want to rewrite this as 1/4 x to the negative 2 in order to take the derivatives. So this becomes the limit as x approaches 0 from the right of ln of x. And this is 1 over 4 times 1 over x squared, or 1/4 x to the negative 2. And that's just going to be easier to take the derivative now. Okay, so this becomes equal to the limit as x approaches 0 from the right. The derivative of ln of x is 1 over x over, and then this would be 1/4 times negative 2 x to the negative 3 power. Okay, so this is the limit as x approaches 0 from the right of 1 over x over, and this becomes negative 1/2 times, or negative 1 over 2 x cubed, right? Because this x to the negative 3 becomes 1 over x cubed. Okay, so now what I'm going to do is I'm going to clear out the complex fraction by multiplying by 2x cubed over 2x cubed. And that would give us the limit as x approaches 0 from the right of, and this would be left on top with 2x squared over just negative 1. Okay, so this becomes negative 2x squared. So this becomes the limit as x approaches 0 from the right of negative 2x squared. Can we do a direct substitution? Can we just put 0 in here and do the calculation? Sure. 0 squared is 0 times negative 2. That'd be 0, right? So this winds up being equal to 0. But Mr. Mitchell, you said 0 times negative infinity isn't always. Yeah, but a lot of times it is. When we multiply 0 times infinity, any type of infinity, a lot of times we do get 0, but not every single time. And I know you're thinking it. I'm going to give you the next problem is going to involve it where it doesn't. All right. All right. To show you that, hey, that's kind of weird. 0 times something doesn't always equal 0. 0 times a number, a real number, always equals 0, but not 0 times infinity. All right. So let's do the next problem. So for this next problem, we have the limit as x approaches infinity of x, sine of 1 over x. And so as x approaches infinity, this first term right here is going to become infinity. So this is going to be infinity. And we're going to be left with sine of 1 over x. But as x approaches infinity, this denominator is going to become really big, which is going to cause this to get closer and closer to 0. So this would be times sine of 0. All right. And sine of 0 is 0. So this is infinity times 0. Okay. So since it's infinity times 0, this is a chance where we can apply L'Hopital's rule. Not quite as it is. Okay. We've got to figure this out first. Okay, so this is equal to, how do we rewrite this as a quotient, right? Because that's what we have. We have a product. Every time a product can be rewritten as a quotient, okay? All right, so what we want to do is you always want to get rid of like the x or the x squared or this like a polynomial right here, because a lot of times that's what this is going to be. One of them is going to be a polynomial and one of them is going to be a function, okay? So you want to get rid of this one. So what I'm going to want to do is I'm going to take the limit as x approaches infinity of x sine of 1 over x. And the version of 1 that I'm going to multiply by is 1 over x over 1 over x. Okay, main fraction bar right there. Because when I go to multiply this, this is going to become 1, right? And so we wind up with the limit as x approaches infinity of sine of 1 over x over 1 over x. Okay, so now what happens with this, I'm going to switch colors for this, okay? When we take the limit as x approaches infinity of the numerator, that would be this. Okay, as x gets really, really big, 1 over that becomes really, really close to 0. And as this gets closer to 0, the sine function gets closer and closer to 0. So this is equal to 0. And the limit as x approaches infinity of 1 over x, well, this is getting really, really big. So this is getting really, really close to 0 also. Okay, so we have 0 over 0, right? So this causes it to, when we do this, when we do this step right here and create the complex fraction, we're actually creating it and forcing it to be 0 over 0 or infinity over infinity. All right. Okay, so then the next thing is, let's clean this up a little bit so that we can take the derivative a little bit easier. So 1 over x I would rewrite as x to the negative 1. So this becomes the limit as x approaches infinity of sine of x to the negative 1 over x to the negative 1. And now that's equivalent to this. So now we can just take the derivative of this and the derivative of this, because we've already stated this. Okay, so this becomes the limit as x approaches infinity. And sine of x to the negative 1 is cosine of x to the negative 1 times, and the derivative of this would be negative 1 x squared. X to the negative 2, rather. Whoops. Okay, so negative 1 x to the negative 2. All right, over, and this becomes negative 1 x to the negative 2. All right, and these two cancel out, right? So you're left with, I'm going to come off to the side here, you're left with the limit as x approaches infinity of cosine of x to the negative 1. Or we're left with the limit as x approaches infinity of cosine of 1 over x. This is going to get closer and closer and closer to 0. So in essence, we're finding cosine of 0, and cosine of 0 would be 1. So here we go. So here's an example of infinity times 0 is not 0. In this case, infinity times 0 is actually the number 1. Crazy stuff. Crazy stuff. So the next situation where we could use L'Hopital's rule is when we get some type of infinity minus some other type of infinity. Okay. Now, don't think because it says here positive infinity minus positive infinity that it has to be that. It's just an infinity minus some other infinity. So this could be a positive or a negative. So this next example, we're finding the limit as x approaches 1, right? But as x approaches 1, the natural log gets closer and closer to 0. But from one end, it's above, okay? And from the other side, it's below. So one of these is going to be, so this is getting closer and closer to 0. This whole thing is going to go to infinity. But which infinity? Positive infinity or negative infinity? and it depends on which side of 1 you're approaching, okay? So really my point of this is this, when we take the limit as x approaches 1, this could be positive infinity. It also could be negative infinity. So I'm just going to write in parentheses plus or minus infinity, okay? It doesn't matter which infinity, the fact that it's an infinity, okay? And then minus, and here's, if we try to do direct substitution, this becomes 1, right? But this really, or not becomes 1, becomes 0, all right? So this, what it means is this is really, really small number. But if x is bigger than 1, then this is going to be positive. And so this would be positive infinity. But if x is less than 1, this is going to be negative, and then this would be negative infinity. So this is, again, minus, and we'd write plus or minus infinity. But it's not the fact that it's, it's just that this is infinity minus another type of infinity. That's what's important, okay? Which allows us to rewrite this, and it's going to allow us to figure out what the limit actually is, okay, when it takes on this form. All right, so what we're going to do is basically we're going to subtract these. So we need to get a common denominator. And if I get a common denominator, I'm going to have a quotient, and then I'm going to be able to use L'Hopital's rule. That's the idea behind it, okay? So this is equivalent to the limit as x approaches 1 of 1 over ln of x. And for this one, I need to multiply by x minus 1 over x minus 1. And then minus 1 over x minus 1. And for this one, I'm going to need to multiply by ln of x over ln of x. Okay, so then this becomes the limit as x approaches 1 of 1 times x minus 1 would just be x minus 1 over, I'm going to write this x minus 1 first. So it'd be x minus 1 ln of x. Don't cancel these x minus 1s. I mean, they could cancel, but don't, because then you'll lose your common denominator. And then minus, and this would be ln of x over x minus 1 ln of x. And you see now we have a common denominator, which means we can subtract. So this would be the limit as x approaches 1 of x minus 1 minus ln of x over, and this would be x minus 1 ln of x. Okay, so now, all right, if we try to plug 1 in here, we're going to get 1 minus 1, which is 0, minus ln of 1, right, which would be 0. So this would be, this comes out to be 0. So I'm going to write the limit as x approaches 1 of x minus 1 minus ln of x. If we put 1 in, we get 1 minus 1 minus 0, right? So that'd just be 0. And the limit as x approaches 1 of x minus 1 ln of x. Well, this would be 0, and this would be 0. So 0 times 0 is 0. Okay. And so now, okay, we can apply L'Hopital's rule, right? But to apply L'Hopital's rule, I'm going to take the derivative of this, the derivative of this, and the derivative of this. This one down here, I'm going to have to apply the product rule. Okay. So this is equal to the limit as x approaches 1 of the derivative of x would be 1 minus the derivative of 1, which is 0, and then minus the derivative of ln of x, which is minus 1 over x. Over, okay, so the derivative of this one would just be 1 times ln of x, so that would just be ln of x. And then plus x minus 1 times 1 over x. All right, and so cleaning this up a little bit, this would equal the limit as x approaches 1 of 1 minus 1 over x over ln of x plus x minus 1 over x. And so what I'm going to do is I'm going to multiply to clear out my complex fraction here by x over x. Okay, so when we do that, we get the limit as x approaches 1 of x minus 1 over, and when we do this one, we get x ln of x plus x minus 1. And let's see what happens. We get, well, if we try to do direct substitution, we're going to get 1 minus 1 in the top, which would be 0. Okay. And this would be 1 times 0. So we're going to get 0 over 0 again, right? So we got to apply. Okay. So this is an example of it. You got to apply L'Hopital's rule again. Okay. So for this one, we got to do the limit as x approaches 1 of x minus 1. That comes out to be 0. And we also have the limit as x approaches 1 of x ln of x plus x minus 1, and that also turns out to be 0. So we can apply L'Hopital's rule to this. So this is equal to, what a pain, huh? Limit as x approaches 1 of, okay, so the derivative of this would be 1. So now L'Hopital's rule is that we're not going to be able to apply L'Hopital's rule anymore because we've got a 1 up here, right? Okay, so we won't have to do it like a third time. Okay, so and then the derivatives. Okay, so I got to apply the product rule for this. So the derivative of x would be 1 times ln of x. So that would just be ln of x and plus x times 1 over x and then plus 1 and then minus 0, so I won't have to write that. And this becomes 1. So this becomes the limit as x approaches 1 of 1 over ln of x plus 1, or the limit as x approaches 1 of 1 over ln of x plus 2. And now we do the direct substitution. Ln of 1 would be 0. So this becomes 1 over ln of 1 plus 2. And that's 1 over 0 plus 2. So this becomes 1 over 2. All right, so this limit from all of this work turns out to be just 1/2. Okay, so we had, so this is a pretty extensive problem, right? Okay, so let me zoom out a little bit. Okay, so we had to first establish that it was some type of infinity minus some other type of infinity. Then the idea is I got to rewrite this as a quotient. Okay, and the way you can do that with these is to actually get a common denominator and subtract. Okay, which is what we did. And then we cleaned it up, worked it out, and then we realized, oh, we can, if we try to do the direct substitution, we're going to get 0 over 0 again. Okay, so then take the derivative again and just work it all out. Okay. All right, we have one more problem to do. All right, and then we'll be done. So for this next problem, we're finding the limit as x approaches infinity of ln of 2x minus ln of x plus 1. So the limit of a difference like this, we can take the limit as x approaches infinity of this minus the limit as x approaches infinity of this. And then what we wind up with, if we do that, okay, as x gets bigger, 2x gets bigger, which means what we're putting into ln of x is getting bigger and bigger and bigger, right? So that means as x approaches infinity of ln of x, ln of x goes to infinity also. So this would be infinity minus, and this one, as x goes to infinity, this is going to infinity. Well, when the input for ln goes to infinity, the outputs also go to infinity. Same reasoning as this one's, just different. Okay, so we have the situation where we have a positive infinity minus positive infinity. Okay, so how do we go about rewriting this one? Because the idea here is still you got to write it as a quotient. Okay, and so there's a property of logarithms, okay, that says if you have the log of something minus the log of something, what you can do is rewrite that as the natural log of the first difference, right? The argument here, 2x over x plus 1. I don't know if you remember that, but I'll write down the log property that we use in just a second, okay? So what this turns out to be is the limit as x approaches infinity of, and this becomes a single logarithm of 2x over x plus 1. Okay, and what I used to determine this was a property of logarithms that we haven't looked at in a while. That says if you have, natural log, it doesn't determine, it doesn't have to be natural log, any type of log with the same base would work. So natural log of A minus the natural log of B, that's always equal to a single logarithm of A over B. And so in this case, our A was the 2x and our B was the x plus 1. Okay. All right, so now we're taking the limit of a function, and there's a function within that function, right? So this is a composition of functions, all right? So we're doing a lot with this problem, okay? So what we can do is we can take the natural log of the limit as x approaches infinity of 2x over x plus 1, okay? And so what I'm using there, what property is that if we take the limit as, and it, again, that doesn't matter, that's infinity, of a composition f of g of x, then that becomes f of the limit as x approaches infinity of g of x. Okay, so now if we try to do direct substitution, this is going to be infinity, and this is also going to be infinity. So that's where we pick up infinity over infinity. Okay, so we need to show this, that the limit as x approaches infinity of 2x is equal to infinity, and the limit as x approaches infinity of x plus 1 is also infinity, which means to this inside here, I can apply L'Hopital's rule, okay? Because I have the limit of something that's going to be infinity over infinity. So we're going to take the derivative of this over the derivative of this, okay? It's keeping this natural log intact, okay? So this becomes the natural log of, and this becomes the limit as x approaches infinity of 2 over, and then the derivative of x plus 1 would be 1. Well, as x approaches infinity, this is going to be 2. So this just turns out to be the natural log of 2. And that's what the limit is for this, all right? So, and here's another crazy thing. Like, you would think infinity minus infinity is, this should be 0, Mr. Mitchell, because, you're subtracting two things that are the same. Well, these infinities might not be the same. There's some infinities that are bigger than other infinities. So when you go to subtracting, it doesn't always come out to be 0. Sometimes it does, sometimes it doesn't. All right. Crazy math. Okay. It's true. I mean, what we did is right. It's just like, you would think that that would come out to be 0, but it doesn't, right? It comes out to be an actual number, natural log of 2. All right. This kind of stuff blows me away that somebody actually figured all this stuff out. All right. All right, you guys, we'll meet back. All right. Or if you're in my other class, I'll see you tomorrow. Okay. All right.